They told him it was impossible. The engineers at Wright Field said no aircraft that size could maintain cabin pressure above 30,000 feet. The metallurgists said the fuselage would crack under the stress. The production managers said even if he solved the technical problems, American factories could never build such a complex machine at scale. But on November 21, 1942, when the first B-29 prototype lifted off from Boeing Field in Seattle, George Schairer's pressurized cabin design was about to change the physics of strategic bombing forever. The test pilot that morning, Edmund Allen, climbed through altitude bands that would have left an unpressurized crew gasping for oxygen and fighting hypoxia. At 10,000 feet, the cabin pressure held steady. At 15,000 feet, the instruments showed no leaks. At 20,000 feet, Allen removed his oxygen mask inside the cockpit and breathed normally while flying an aircraft the size of a small building through air so thin that exposed skin would freeze in seconds. The impossible had become real. But the true test would not come in the skies over Washington state. It would come 2 years later, over Japan, where enemy pilots in their fastest interceptors would climb desperately toward American bombers that cruised in an altitude band no defending fighter could reach. The Japanese would watch their altimeters approach their aircraft's ceiling, watch the B-29s continue upward, untouchable, and understand that American engineering had created something beyond their ability to counter. The psychological impact of that realization, of watching your enemy operate with impunity in airspace you could not defend, would be as devastating as the bombs themselves. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem Schairer had been asked to solve in 1941 seemed straightforward on paper. The Army Air Forces wanted a bomber that could fly higher, faster, and farther than anything in existence. They wanted it to carry 5 tons of bombs across 2,000 miles of ocean, strike targets in Japan, and return to base. Most critically, they wanted it to operate at altitudes where enemy fighters and anti-aircraft fire would be ineffective. The specifications called for operational ceiling above 35,000 feet. No bomber in production anywhere in the world could reach that altitude with a full combat load. The physics were unforgiving. At 30,000 feet, atmospheric pressure drops to roughly 4 pounds per square inch compared to 14.7 pounds at sea level. The temperature hovers around -40 degrees Fahrenheit. Human beings cannot survive in such conditions without supplemental oxygen and protective equipment. Bomber crews in existing aircraft wore oxygen masks, heavy flight suits, and heated gloves. They endured hours of cold and hypoxia that degraded their performance and endangered their lives. Frostbite casualties were common. Oxygen system failures killed crews without warning. The human body was not designed to function at those altitudes. Schairer's solution was radical. Instead of requiring the crew to adapt to the hostile environment at altitude, he would bring sea-level conditions inside the aircraft. He would build a pressurized cabin, maintaining comfortable atmospheric pressure even as the bomber flew through the stratosphere. The crew would work in shirtsleeves, breathing normally, their efficiency unimpaired by cold and oxygen deprivation. It had never been done on an aircraft this large. The engineering challenges were immense. The concept of cabin pressurization was not new in 1941. Wiley Post had experimented with pressurized suits for high-altitude flight in the 1930s. Lockheed had built the XC-35, a small, experimental aircraft with a pressurized cabin, in 1937. But those were research projects, one-off designs built to prove concepts. No one had attempted to pressurize a combat aircraft weighing over 100,000 pounds with a wingspan of 141 feet. The scale changed everything. A pressurized fuselage must be airtight. Every rivet, every seam, every access panel must seal perfectly against the pressure differential between inside and outside. On a small aircraft, this is manageable. On the B-29, with its fuselage sections built in different factories and assembled on the flight line, maintaining airtight integrity seemed impossible. The fuselage had to be strong enough to contain pressure differential of 8 pounds per square inch, essentially turning the aircraft into a flying pressure vessel that would expand and contract with every altitude change. The stresses would be enormous, cyclic, and potentially catastrophic if the structure failed. Schairer and his team at Boeing approached the problem methodically. They divided the B-29's fuselage into 3 pressurized sections. The forward section housed the pilots, flight engineer, bombardier, and navigator. The rear section contained the gunners who would operate the defensive armament. A long, unpressurized bomb bay separated the 2 pressurized compartments. Crew members could move between sections through a crawl tunnel that ran above the bomb bay, 34 inches in diameter, barely wide enough for a man to squeeze through while wearing a parachute. The forward cabin received the most attention. This was where the pilots would spend 12 to 15 hours on a typical mission to Japan and back. The space needed to be functional, with room for all the controls, instruments, navigation equipment, and crew stations required to operate the most complex bomber ever built. But it also needed to be livable. The Army Air Forces had learned from earlier high-altitude missions that crew fatigue degraded bombing accuracy and endangered aircraft. Men who were cold, exhausted, and hypoxic made mistakes. The pressurized cabin would eliminate those problems. Boeing engineers designed the forward cabin to maintain pressure equivalent to 8,000 feet altitude, while the aircraft flew at 30,000 feet or higher. At 8,000 feet, humans can breathe normally without oxygen masks. The temperature could be controlled through heating systems that drew warm air from the engines. The crew would work in reasonable comfort, their cognitive functions unimpaired, their manual dexterity unaffected by cold and oxygen deprivation. In theory, this would make the B-29's crew far more effective than crews in unpressurized bombers like the B-17 or B-24. The structural engineering required to make this work was unprecedented. The fuselage skin had to be thicker and stronger than on conventional bombers. Boeing specified aluminum alloy sheets up to 0.08 inches thick in critical areas, compared to 0.04 inches on earlier designs. The frames and stringers that gave the fuselage its shape had to be reinforced. Every penetration in the pressure hull, every window, every gun port, every access hatch required special seals and locking mechanisms. The engineers calculated stress loads, pressure cycles, and fatigue limits. They built test sections and subjected them to pressure cycling that simulated thousands of hours of flight. Some sections failed. The designs were modified and tested again. By mid-1942, Boeing had a design that worked on paper and in limited testing. Now came the harder challenge, building it in quantity. The Army Air Forces wanted B-29s in combat as quickly as possible. They projected requirements for thousands of aircraft. Boeing's plant in Seattle could not possibly produce them fast enough alone. The solution was to expand production across multiple factories, each building major sub-assemblies that would be shipped to final assembly plants. It was an ambitious plan that would test American industrial capacity. 3 major final assembly plants were established. Boeing's facility in Wichita, Kansas, would be the largest producer. Bell Aircraft's plant in Marietta, Georgia, would build the aircraft under license from Boeing. Martin's facility in Omaha, Nebraska, would contribute additional production. Thousands of subcontractors across the country would manufacture components, from engines to instruments to landing gear. The supply chain would have to coordinate delivery of hundreds of thousands of parts to ensure smooth assembly. Any bottleneck could halt production. The pressurization system made everything more complicated. Workers had to be trained in sealing techniques that had never been used in aircraft production before. Quality control inspectors had to verify that every seal was perfect, every rivet properly set, every joint airtight. The tolerances were tighter than anything required in conventional aircraft construction. A tiny leak that would be insignificant in an unpressurized bomber could make the pressurization system fail in the B-29. The workers were building to standards that seemed excessive until they understood what happened at altitude if the cabin lost pressure. The early production aircraft revealed problems immediately. Leaks appeared around windows, gun ports, and access panels. Some fuselage sections developed cracks under pressure cycling. The crawl tunnel between forward and rear cabins proved difficult to seal properly. Boeing engineers made modifications on the fly, changing designs as aircraft moved down the assembly line. Workers retrofitted earlier planes with fixes developed for later ones. The learning curve was steep and expensive. Aircraft that should have been combat-ready sat on airfields while crews fixed pressurization problems. General Henry Arnold, commanding the Army Air Forces, grew increasingly frustrated with the delays. He had promised President Roosevelt that B-29s would be bombing Japan by mid-1944. The pressurization problems threatened that timeline. In March 1944, Arnold visited the Wichita plant and reportedly told Boeing executives that he expected results immediately, regardless of the technical difficulties. The pressure on engineers and production workers intensified. They worked around the clock, testing solutions, implementing fixes, pushing aircraft toward combat readiness. By May 1944, the problems were largely solved. The production aircraft maintained cabin pressure reliably at operational altitudes. The sealing techniques had been refined. The structural modifications eliminated most of the cracking issues. The B-29 was ready for combat. But the crews who would fly these aircraft into battle did not yet understand what advantage Schairer's pressurization system would give them. They would learn over Japan, where Japanese pilots would climb toward them in increasingly desperate attempts to defend their homeland, only to discover that American bombers cruised in airspace their fighters could not reach. The Japanese understood high-altitude interception was critical to homeland defense long before the B-29s arrived. In 1943, as American forces advanced across the Pacific, Japanese military planners recognized that strategic bombing of the home islands was inevitable. They tasked their aircraft manufacturers with developing interceptors capable of reaching 35,000 feet and engaging enemy bombers at those altitudes. The results would prove inadequate. The Nakajima Ki-44 Shoki, called Tojo by Allied intelligence, was designed specifically as a high-altitude interceptor. It entered service in 1942 with a Nakajima Ha-109 engine, producing 1,520 horsepower. In theory, the Ki-44 could reach 36,000 feet. In practice, the climb to that altitude took over 20 minutes, and the aircraft's performance at extreme altitude was marginal. The controls became sluggish in the thin air. The rate of climb near ceiling dropped to less than 300 feet per minute. Most critically, the engine lost power rapidly above 30,000 feet, making it nearly impossible to accelerate for attack runs or maneuver during combat. The Kawasaki Ki-61 Heian, known as Tony, used a license-built Daimler-Benz inline engine that produced 1,175 horsepower. Japanese engineers had chosen the inline design specifically for high-altitude performance. The Ki-61 had a service ceiling listed at 37,000 feet, impressive on paper. But the Kawasaki engine suffered chronic reliability problems. Overheating was common. The cooling system struggled in tropical climates and during extended climbs. Many Ki-61 pilots reported engine failures during attempted high-altitude interceptions. Even when the engine functioned properly, the aircraft took nearly 30 minutes to climb from ground level to 35,000 feet, by which time the enemy bombers had already completed their bomb runs. The Nakajima Ki-44 Hayate, introduced in mid-1944, represented Japan's most advanced fighter design. Allied pilots called it Frank. The Ki-84 had a Nakajima Ha-45 engine with 1,890 horsepower, giving it excellent performance at medium altitudes. Its service ceiling was officially 34,600 feet, but this figure was theoretical maximum altitude, not operational combat ceiling. At 34,000 feet, the Ki-84 could barely maintain level flight. Climbing higher was impossible with combat load. The aircraft lacked the engine power and wing loading to fight effectively above 30,000 feet. Mitsubishi's J-2M Raiden, called Jack, was another interceptor designed specifically to counter high-altitude bombers. It featured a turbocharged Mitsubishi Kasei engine producing 1,800 horsepower. The turbocharging should have given the J-2M excellent high-altitude performance. Instead, the complex turbocharger system proved unreliable. Pilots reported frequent mechanical failures. The turbocharger ducts were vulnerable to combat damage. When the system worked, the J-2M could reach 38,000 feet, but climb time was excessive, and combat capability at altitude was limited by control, sluggishness, and reduced engine response. Every Japanese interceptor faced the same fundamental problem. They were designed to meet a specification that looked achievable on paper, but proved nearly impossible to meet in operational conditions. The service ceiling listed in technical documents represented the absolute maximum altitude the aircraft could reach under ideal conditions. Light fuel load, no ammunition, no combat maneuvering, perfect engine tune, experienced test pilot. Combat interceptions required fuel for extended patrols, full ammunition load, hard maneuvering during attack runs, and pilots of varying skill levels. Under these realistic conditions, Japanese fighters struggled to reach even 30,000 feet, and their effectiveness above that altitude approached zero. Japanese pilots training for bomber interception missions learned these limitations through bitter experience. Training exercises at high altitude revealed how difficult it was to control their aircraft in thin air. The stick forces increased dramatically. Roll rate decreased. Stall speed increased, leaving little margin between controlled flight and losing control. Engine power dropped so significantly that acceleration was measured in seconds per mile per hour rather than the reverse. Pilots discovered that if they did manage to reach a B-29's altitude, they had almost no energy reserve for combat maneuvering. A single hard turn could bleed off enough speed to cause a stall. Recovery from a stall at 35,000 feet meant diving through thousands of feet of altitude, abandoning the interception attempt entirely. On June 15, 1944, 75 B-29s from the 20th Bomber Command, based in India, launched the first strategic bombing raid against the Japanese home islands since the Doolittle Raid of 1942. The target was the Imperial Iron and Steel Works at Yawata on Kyushu. The bombers flew from staging bases in China, crossing the East China Sea at altitudes between 28,000 and 32,000 feet. Japanese radar detected them 200 miles from the coast. Air defense commanders scrambled every available interceptor. Major Teruhiko Kobayashi led a squadron of Ki-44 interceptors from Suiki Air Base. He had flown combat missions since 1942, accumulating hundreds of hours in fighters. He was experienced, skilled, and confident in his aircraft's capabilities. His briefing that morning had emphasized the criticality of stopping the American bombers. The steelworks at Yawata was vital to war production. He and his squadron mates understood their mission was to destroy as many bombers as possible before they reached the target. Kobayashi's flight climbed aggressively, engines at maximum power. At 10,000 feet, the Ki-44s were climbing at over 3,000 feet per minute. At 20,000 feet, the rate of climb had dropped to 1,500 feet per minute. At 25,000 feet, it was down to 800 feet per minute. Kobayashi watched his altimeter creep upward, while reports from ground control indicated the American bombers were approaching at 30,000 feet. He pushed his throttle forward, coaxing every bit of performance from his engine. His aircraft shuddered in the thin air. The controls felt mushy, unresponsive. At 29,000 feet, Kobayashi spotted the B-29s. They were above him, perhaps 2,000 feet higher, silvery shapes moving steadily toward Yawata. He pulled back on his stick, trying to climb into attack position. His airspeed dropped. The engine labored. He gained altitude slowly, agonizingly. By the time he reached 30,000 feet, The bombers were directly overhead at 32,000 feet. He tried to climb higher. His aircraft would not respond. The engine was producing maximum power, but there simply was not enough air density at this altitude to generate the thrust needed for further climb. Kobayashi attempted an attack anyway. He nosed over slightly to build speed, then pulled up hard into a zoom climb, trading airspeed for altitude. His Ki-44 rose through 31,000 feet. The nearest B-29 was perhaps 500 feet above him, close enough that he could see details of the fuselage, the gun turrets, the massive Schairer 3350 engines. He aimed his guns and pressed the firing button. His aircraft shuddered as the Type 1 machine guns and 20mm cannons fired. The burst went wide. The B-29 continued unperturbed. Then Kobayashi's airspeed bled off completely. His aircraft stalled. The nose dropped. He pushed the stick forward to recover, diving away from the bombers, watching them continue toward Yawata while he fell back toward denser air where his aircraft could fly controllably. He had failed to intercept. The Americans were untouchable. Other Japanese pilots experienced similar frustration that day. Those flying Ki-61 interceptors reached slightly higher altitudes, a few achieving 31 or 32,000 feet, but the B-29s were cruising at 32 to 34,000 feet, just above the Japanese fighters' effective ceiling. Even when Japanese pilots managed to approach the bomber stream, their attacks were ineffective. At extreme altitude, their aircraft lacked the performance needed for proper attack runs. They could not accelerate into firing position. They could not maneuver to avoid defensive fire. They could make one pass, perhaps two if they were willing to risk stalling, and then they had to dive away to regain flying speed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The bomber crews in the B-29s watched these interception attempts with professional detachment. They could see the Japanese fighters far below them, struggling to climb into range. Some fighters managed to get close enough to fire, but their attacks were half-hearted, without the aggressive energy that characterized effective fighter combat. The defensive gunners on the B-29s fired back when fighters approached, but mostly they just watched the Japanese aircraft fall away, unable to maintain altitude for sustained combat. Inside the pressurized cabins of the B-29s, the crews worked in shirtsleeves. The cabin temperature was maintained at comfortable levels through heating systems that drew warm air from engine exhaust. The pressure altitude inside the cabin was 8,000 feet, low enough that no oxygen masks were required. The pilots controlled their aircraft through normal flight controls. The bombardier worked at his Norden bomb site without the distraction of hypoxia or cold. The navigator plotted courses with full mental clarity. The radio operator communicated with other aircraft in the formation without the breathing interference that oxygen masks caused. This was exactly what George Schairer's pressurization system was designed to achieve. The crew's efficiency remained high throughout the mission. There was no fatigue from fighting hypoxia, no frostbite from exposed skin, no degradation of cognitive function from oxygen deprivation. The bomber crews could focus entirely on their mission objectives without the physical challenges that had plagued high-altitude bombing in earlier aircraft. The difference in combat effectiveness was measurable and significant. For the Japanese pilots, watching from thousands of feet below or from brief glimpses during failed attack runs, the psychological impact was devastating. They understood immediately that they were facing an enemy who could operate in airspace they could not defend. The B-29s were not faster than Japanese fighters. They were not more maneuverable. But they flew higher than Japanese interceptors could effectively reach, and that altitude advantage made them nearly invulnerable to conventional fighter interception. Lieutenant Sadamu Komachi, flying a Ki-44 that day, later described his feelings during the failed interception attempt. He had climbed to 32,000 feet, near his aircraft's absolute ceiling. He had spotted the B-29 formation several thousand feet above him. He attempted to climb higher, but his aircraft simply could not perform at that altitude. The engine produced insufficient power. The controls responded too slowly. He made one firing pass, expending precious ammunition with no visible effect on the bombers. Then he had to dive away because his airspeed had dropped dangerously close to stall speed. As he descended, watching the bombers continue toward their target, he experienced what he later called a moment of complete clarity. Japan had no answer to this threat. The Americans had achieved technical superiority in a critical area, and there was no immediate way to counter it. Ground observers watching the Yawata raid saw the same dynamic play out across the sky. Japanese fighters swarmed toward the bomber formation. They climbed desperately. They made sporadic attacks, but the B-29s maintained their altitude and heading, seemingly untouched by the defensive efforts. The fighters that got close enough to attack were operating at the edge of their performance envelope, unable to maneuver effectively, unable to sustain combat. The Americans completed their bomb run, dropped their ordnance on Yawata, and turned for home. Japanese fighters followed them out to sea, still trying to attack, still failing to inflict significant damage. The psychological impact on Japanese pilots, on ground crews, on commanders watching the raid unfold was profound and demoralizing. The failed interception at Yawata was not an isolated incident. It was the first chapter in a story that would repeat itself across the Japanese home islands for the next 14 months. As B-29 operations expanded from China to the Marianas, as bombing raids increased in frequency and intensity, Japanese air defense forces faced the same problem on every mission. They could not reach the altitude where American bombers operated most effectively. In November 1944, the 20th Air Force began operations from newly captured bases in the Marianas. Saipan, Tinian, and Guam became massive air bases housing hundreds of B-29s. These islands were only 1,500 miles from Tokyo, well within the bombers' range. The raids began with high-altitude precision bombing attempts against specific industrial targets. The B-29s typically flew at altitudes between 30,000 and 33,000 feet. Japanese interceptors scrambled to meet every raid. The results were consistently the same. Japanese pilots developed tactics to counter the altitude advantage. Some attempted high-speed diving attacks from maximum altitude, trading height for speed. These attacks were dangerous to execute and rarely effective. The dive had to be precisely timed to intercept the bomber stream. The pilot had to control his aircraft at speeds approaching terminal velocity. The firing pass lasted perhaps 2 seconds. Then the attacker had to pull out of the dive and climb back to altitude, a process that consumed fuel rapidly and left him vulnerable to escort fighters. Most diving attacks missed completely. Those that succeeded in getting firing solutions rarely inflicted significant damage because the time on target was too brief. Other pilots tried coordinated attacks from multiple directions, hoping that simultaneous threats would overwhelm the bomber's defensive fire. These tactics required radio coordination, precise timing, and multiple aircraft operating at extreme altitude. In practice, Japanese fighters struggled to maintain formation at 30,000 feet. The thin air made station keeping difficult. Radio communication was often unreliable. The coordinated attacks devolved into individual efforts, each pilot making his own attack run when he could reach firing position, which was seldom and briefly. The most desperate tactic involved ramming. Some Japanese pilots, recognizing they could not shoot down B-29s effectively, attempted to collide with them deliberately. These ramming attacks required extraordinary courage and almost always resulted in the death of the pilot. They occasionally succeeded in destroying a B-29, but the exchange ratio was unsustainable. Japan could not afford to lose experienced pilots in one-for-one exchanges with American bombers that were being produced at rates exceeding 100 aircraft per month. By early 1945, Japanese air defense commanders recognized that conventional interception tactics were failing. They shifted resources toward night fighting, hoping that darkness would negate some of the B-29's altitude advantage. The Americans responded by conducting both day and night raids, forcing Japanese defenders to maintain continuous alert status. The physical and psychological strain on Japanese fighter pilots became severe. They flew mission after mission, climbing desperately toward bombers they could rarely reach, expending ammunition they could not afford to waste, watching their country burn beneath them while they proved incapable of defending it. The pressurized cabin that George Schairer had designed gave B-29 crews an advantage that extended beyond simple altitude performance. The comfort and efficiency of working in shirt-sleeve conditions meant crews could fly longer missions with less fatigue. A typical mission to Tokyo and back from the Marianas lasted 15 hours. In an unpressurized bomber at high altitude, crews would have been exhausted, hypoxic, and degraded in performance by the end of such a mission. In the B-29, crews remained alert and effective throughout the flight. The operational advantage was measurable in bombing accuracy, crew survival rates, and mission success percentages. American commanders recognized this advantage and exploited it systematically. When Major General Curtis LeMay took command of the 21st Bomber Command in January 1945, he initially continued high-altitude precision bombing operations. The results were mixed. Weather over Japan often obscured targets. High winds at altitude, particularly the jet stream, which was not yet fully understood, scattered bomb patterns. LeMay eventually switched to low-altitude night incendiary raids that proved devastatingly effective against Japanese cities. But the option to bomb from high altitude remained available whenever tactical situations required it, and that option existed only because Schairer's pressurization system worked. For Japanese pilots, the inability to defend their homeland created psychological wounds that went beyond normal combat stress. Fighter pilots are trained to believe in their ability to control outcomes through skill and aggression. They learn that proper tactics, accurate shooting, and aggressive maneuvering can defeat any enemy. The B-29 campaign shattered these beliefs. Japanese pilots discovered that skill and courage were insufficient when the enemy possessed technological advantages they could not overcome. Lieutenant Yasuhiko Kuroe, who flew Ki-44 interceptors throughout 1945, kept a diary that survived the war. His entries from the period of the B-29 campaign reveal progressive demoralization. In January, he wrote confidently about new tactics and training that would improve interception success. By March, his tone had changed. He described the frustration of climbing to maximum altitude only to watch bombers pass overhead, unreachable. In May, he wrote about the smell of burning cities, the knowledge that his family in Osaka was at risk, and his complete inability to protect them. His final entries before the war's end contained no tactical discussions, no optimism, just resignation to an outcome he could not prevent. Japanese ground crews experienced their own form of helplessness. They maintained the fighter aircraft, tuned the engines for maximum performance, checked every system to ensure their pilots had the best possible equipment. Then they watched those pilots take off, climb desperately toward the incoming bombers, and return having achieved nothing. The mechanics understood the technical limitations. They knew the engines were producing maximum rated power. They knew the airframes were sound. The problem was not maintenance or reliability. The problem was that Japanese aircraft were simply incapable of matching American performance at high altitude. No amount of mechanical skill could overcome fundamental design limitations. The civilian population suffered most directly from the B-29 campaign. Tokyo, Osaka, Nagoya, Kobe, Yokohama, and dozens of smaller cities were bombed repeatedly. The incendiary raids that began in March 1945 killed hundreds of thousands of people and destroyed vast areas of urban housing. Japanese civilians watched the bombers overhead, watched their own fighters attempt interception, and understood that their air defenses were inadequate. The psychological impact of this realization, of knowing that enemy aircraft could strike at will while your own military proved incapable of stopping them, was devastating to civilian morale. American bomber crews witnessed Japanese interception attempts with mixed emotions. They respected the courage of pilots who climbed toward them mission after mission, despite overwhelming technical disadvantages. They understood that Japanese pilots were trying to defend their homeland against attack, a motivation any military professional could comprehend. But they also recognized that the technological disparity made the contest unequal in fundamental ways. Some B-29 crew members later expressed discomfort with this imbalance, feeling that they had participated in something less than fair combat. Captain Robert Morgan, who flew B-29s in the Pacific after completing a tour in B-17s over Europe, later described the difference between the two theatres. Over Germany, flak and fighters made every mission a desperate struggle for survival. American bombers faced Luftwaffe pilots in aircraft that were often superior to Allied fighters. The Germans had radar-directed anti-aircraft guns that could reach any altitude bombers could achieve. Every mission resulted in losses. Crews knew that statistical survival through a full tour of duty was unlikely. In contrast, missions over Japan felt almost anticlimactic. Japanese fighters rarely reached effective attack positions. Flak was less accurate and less intense than German defences. The B-29's altitude capability and defensive armament made it relatively safe. Morgan said he felt almost guilty about the disparity. The pressurization system required maintenance and occasionally failed. When cabin pressure was lost at altitude, crews had to don oxygen masks immediately. Emergency depressurization was dangerous, potentially causing decompression sickness if the pressure drop was rapid. Several B-29s experienced pressurization failures during missions, forcing them to descend to lower altitudes, where crews could breathe without supplemental oxygen. These aircraft became vulnerable to Japanese interceptors at medium altitudes. Several were shot down after losing cabin pressure and descending into the altitude band where Japanese fighters could operate effectively. The crews who experienced these failures gained new appreciation for what the pressurization system provided. Flying in shirtsleeves at 30,000 feet seemed normal until you had to do it the old way, with oxygen masks and heavy flight gear and constant awareness of hypoxia risk. George Schairer's pressurization design for the B-29 influenced commercial aviation development in the post-war period. Boeing's engineers had solved problems of structural integrity, sealing techniques, and pressure cycle management that would prove directly applicable to passenger aircraft. The Boeing 307 Stratocruiser, introduced in 1947, used a double-lobe fuselage design derived from B-29 pressurization technology. Passengers could fly in comfort at altitudes above weather and turbulence. The Douglas DC-6 and Lockheed Constellation adopted similar pressurization systems, making long-distance air travel practical and comfortable. The military lessons from the B-29 campaign shaped strategic bombing doctrine for decades. The United States Air Force, established as an independent service in 1947, built its strategic deterrent around high-altitude bombers carrying nuclear weapons. The Convair B-36, Boeing B-47, and Boeing B-52 all featured pressurized cabins and high-altitude performance. The assumption was that altitude provided protection from interception, just as it had over Japan. This assumption proved less valid as surface-to-air missiles developed in the 1950s, but the engineering expertise in pressurization remained relevant for all high-altitude aircraft. Japanese aviation engineers studied captured B-29s after the war, examining the pressurization systems in detail. They recognized the sophistication of the design and the manufacturing precision required to build such systems reliably. The technology gap that had been so painfully evident during the war became a focus of post-war development. Japan's aircraft industry, rebuilt after 1950 under different economic and political conditions, eventually mastered pressurization technology and other advanced systems. But during the war, that gap had been unbridgeable. The strategic impact of the B-29 campaign on Japan's ability to continue the war was substantial. The destruction of urban areas, the disruption of war production, the mining of harbors, and the psychological effect of undefended bombing all contributed to Japan's decision to surrender in August 1945. The atomic bombs dropped on Hiroshima and Nagasaki were delivered by B-29s, aircraft whose pressurized cabins and high-altitude performance made them ideal for this mission. The crews flew in shirt-sleeve comfort to their targets, operated their equipment with full efficiency, and returned to base. The mission profile that George Schairer's design made possible ended the war. Looking back from the present, the B-29 campaign illustrates how specific technical innovations can have strategic consequences. Schairer did not invent pressurization. He applied existing concepts to an aircraft larger and more complex than anyone had attempted before. He solved engineering problems that seemed impossible. He created a system that worked reliably in production aircraft, built by tens of thousands of workers across multiple factories. His achievement was not a laboratory curiosity or experimental prototype. It was a practical, operational capability that changed the strategic balance in the Pacific War. The Japanese pilots who climbed desperately toward unreachable bombers, the American crews who worked in comfort at altitudes their enemies could not defend, and the engineers who made it all possible were participants in a transformation of warfare. High-altitude strategic bombing became practical because pressurization made it sustainable. The human cost of that transformation was measured in burning cities and failed interceptions, and the psychological weight of helplessness experienced by defenders who could not protect their homeland. When Edmund Allen lifted off from Boeing Field on that November morning in 1942, breathing normally without an oxygen mask at 20,000 feet inside the B-29 prototype, he proved that the impossible was achievable. 2 years later, over Japan. That achievement translated into strategic advantage that Japanese forces could not counter. The engineering triumph that began with Schairer's blueprints ended with American bombers cruising untouchable above 30,000 feet, while Japanese interceptors climbed uselessly below them and cities burned. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.